Thank you, Davide, for the introduction. So, hi everyone, my name is Filippo Carloni, and I am a third-year PhD student here at the Polytechnic in Milano. And today I will present you one of the work in which I'm focusing on the last year, that is one Automaton to rule them all, beyond multiple regular expression execution, on which I work together with Luisa Ciccolini, Davide Conficoni, and Marco Domenico Sant'Ambrogio. So before to start about talking the idea, I want to give you a brief introduction about what we mean about pattern matching in usual scenarios. Usually we have these patterns that, as we can imagine it, are called regular expression, and we want to find this pattern in a stream of data, a set of data, because we want to spot specific characteristics on this data. For instance, in network intrusion detection system based on signature, we want to analyze the network traffic entering in a private network with respect to a set of malware signatures, a set of rules that helps to stop and identify potential intrusion in this network. So the most common representation of this pattern, the user-friendly way, is about using regular expressions, while when we move to the recognizing step, we want to look at the finite state automaton. However, as in the case of Snort or Suricata, that are network intrusion detection system, or proteomics, usually have a lot of regular expressions, so patterns that we want to identify with respect to a single data. And this is the problem, because usually this implies a lot of states, a lot of memory usage, and for sure, a high latency that is not always achievable, for instance, in the case of filtering packets. So from this observation comes the idea on, we do better about in looking at a single dataset? And this is the idea about, there are some similarities between these patterns in a benchmark, in a dataset. So we started trying to quantify, at least in a tentative way, this type of similarities, and with the Indel similarity index. And we can see that there is a quite high similarity in these most common benchmarks, for instance, in Automata or in TCP, that are, the last one is intrusion detection, which the first one is about proteomics. And thus comes the idea. We want to propose a new model to try to merge together a set of regular expression in trying to optimize both the memory efficiency and the latency. Then we propose a way to compile the regular expression into this new type of representation. And finally, we want to evaluate the impact of the new model in the execution perspective. Coming back to the idea in how to identify, in how to merge this type of set of regular expression into a single new automata, I start these two representative regular expressions that are general exemplification, in which we have the starting regular expression and a common sub-patterns, some common sub-patterns that are shared from the regular expression 1 and the regular expression 2. Then we want to put together these two patterns and, of course, the merged part together without repeating this type of sub-patterns. However, as we can see from the graph, from this representation, we then created new lines with respect, new edges, so new connection between states with respect to the starting regular expression. For instance, we have the path from 1 to 2 to state 2 to 3 and then to 4, or we can go from 2 to 4. However, it's not intended to go from state 2 to state 4 in the initial regular expression 1. And this is the problem, because in this way, we are allowing new false positive, new representation, new accepted language that are not accepted from the native regular expression taken in input. And thus come our idea about developing an activation function. An activation function has the concept that keep tracks of which regular expression are merging during the traversal of the automaton, and if that type of regular expression can go further with respect to an edge with respect to another. So basically, we are keeping which regular expression are matching and which regular expression can go further in the traversal of the automaton if they are allowed. In this way, we remove the problem of patterns that cannot be taken from a regular expression with respect to another. So coming back to what composes the model. We have as in the classical finite state automaton, we have the states, the alphabet, which represent which characters we can analyze. Then we have the initial states. In this case, are the initial state of each regular expression that we want to recognize. Then we have the final states, representing when a match occurs, when we reach that final states. We have, as a classical FSA until now, also the state transition, so how an automaton can move further from a state to another. But with respect to the standard FSA model, we have with the MFSA, the FSA activation function, which, as anticipated, keep tracks of which regular expression are matching and which regular expression can go further in the matching of the single traversing in the automaton. And of course, the set of identifier for the regular expression that we are considering. This represents the first contribution, that is a novel formalization of the class with respect to the standard FSA representation to support this concept of merging regular expression together in a single automaton. And then we have how to compile a representation that is a regular expression into an MFSA. First of all, we have the syntax and lexical analysis. So basically, we take the regular expression as input, we check if they are well formed, and then we move to the FSA generation. Until these steps, we are looking at the regular expression singularly. Then we move to the merging operation that basically takes a set of regular expression and puts together this regular expression in a single novel MFSA automaton representation. The set, how many regular expression we want to match together is the merging factor that we will see in the experiment can be increased with respect to how many regular expression we want to put together. This represents the multi-level compilation framework that is the second contribution of this work. But then we have to analyze on how to match the data with respect to this new model. So let's start with an example. We have two simple regular expressions. This first one that matches basically C, B, A, and B characters. And then we have the second regular expression and the representative automaton that matches A followed by B or C. And these are the two equivalent representation in automaton language. Moving now to the MFSA representation, we can consider first that we have reduced also in this exemplification the number of states and transition. And however, now we have to consider multiple regular expression when traversing this automaton. For instance, starting from the string to match in input that is S, we have first of all A that activates the second regular expression in the state 4. Then we have the C that basically conclude with a match for the second regular expression, but also activate the first one regular expression in the state 1. Then we have a B that moves forward in the matching of the regular expression 1. Then we have another A that in this case activate both the transition for state 4 to 5 for the regular expression 1, because in the path to match that started from state 1, but also activate against what is the regular expression 2. So in this case, we have an activation set that is composed from regular expression 1 and 2. Finally, we have a B that represents a match for both the languages. And so we have a double match also in this case. So finally, we have 3 matches, 1 from regular expression 1 and 2 from regular expression 2. That is achieved only with a single pass in this automaton. And this is the point about using MFSA. We then implemented this type of idea in Infant, that is one of the most famous and state-of-the-art algorithm about non-deterministic finite state automaton execution on parallel architecture. And then we checked that it guarantees the same accuracy. And of course, we evaluated how the latency changed while employing or not the MFSA model. So coming to the experimental evaluation, first of all, we evaluated how much is the impact about introducing this merging step compilation, which is the compression ratio that can we achieve in using MFSA with respect to keeping the standard FSA representation, so having 100 of regular expression with respect to the compression version. Then we have evaluated the infant execution on a desktop CPU to keep track of which is the latency improvement or decreasing with respect to the standard execution. So starting from the compilation time overhead, we can see that the compilation time is quite low. However, in the current implementation of the merging procedure, we have a sub-exponential compilation time. If it's possible to pay this small overhead in compilation, you can see that starting from the state compression, while increasing the merging factor, we can achieve a top geometric mean average that is about 70% in state compression with respect to not having compressed the automaton or the regular expression equivalent representation. And this is, first of all, what it does imply a reduction in memory utilization, because we are basically representing the 70% less of the state with respect to the standard representation of one automaton. Coming now to how much is the latency with respect to the classical implementation. First of all, we evaluated this model in a single thread configuration. So basically we have one single thread while we trying to increment how many regular expressions we are merging in the new model. So the first one, the merging factor equals to 1, meaning no merging factor. Basically, we are looking at single automaton. Then we have to merging factor equals to all. That means basically, in this case in this evaluation, 3 under the regular expression merged together. And we can see that usually we reach a sort of plateau in how much we can reduce the execution times. And usually it is the merging factor equals to all for at most all benchmark. Exceptionally, .*9 and Automata have a better improvement while keeping a lower merging factor. However, looking also in this case at the top configuration, we have a geometric mean improvement in the single time evaluation that is about 5.3 per with respect to the single thread evaluation with the native FSA evaluation. So no merging factor with respect to our proposal. Now moving to more real scenarios in which we have also a processor which can exploit an increasing number of threads. In this case, is a desktop processor with 4 core and 8 threads. You can see that this naive approach, so the standard approach in which we have a lot of FSA and a lot of thread, we reach a sort of plateau in the number of achieving in the lowering the execution time, so the latency. And of course, we stay usually on the number of threads that is from 4 to 8, because it's the core limit of the architecture. However, if we propose the execution of MFSA, you can see that we can lower this latency in 2 types of configuration. The first one is about keeping the same throughput. We can see that if we want only to keep the same throughput, we can reduce, in average, we can halve the number of threads that we want to use. And this evaluation is on the blue circles. Then if we have no limits in about how many threads we want to use, and we want to achieve the maximum number of MFSA and threads, so we want to have the lowest latency in absolute values, we can see that in red, we can lower with a geomean speed up in top configuration that is about 4 per with respect to not having used the MFSA model and in the multi-thread evaluation. So basically we have an improvement in 2 different types of experiment. One is we want to achieve the same throughput, but we want to use lower thread, and this is possible using MFSA. And we want also to achieve a lower execution time using how much as thread as possible, and we can do this using MFSA. Looking at the future, we are working on improving the MFSA algorithm. We want to lower the plateau that we can reach in executing of MFSA in infant. We want for sure reduce the impact of the merging procedure in the compilation time, and we are looking at trying to possibly support advanced feature in regular expressions that are not classically supported from standard FSA model. This concludes my presentation. If you are interested, feel free to have a look at the code or the preprint paper that is available on GitHub. And thank you for the attention.
I have a question for you. So please elaborate a bit more on why on some benchmarks, we have seen that the merging factor of the whole rule set is not the optimal one.
You are referring to this picture, right?
Yes.
Okay. So we are a bit strange when we see that, of course, the merging factor equal to all is not the best case, but as I anticipated, when we traverse automaton, we have to keep track of how many regular expressions we are merging. And we also see that in this type of benchmark, so .*9 and Automata, have the problem that they are already a large number of active transition for in the single FSA evaluation. So adding in this case an overhead about how many regular expression can keep active during the traversal of the automaton has reduced the maximum number of regular expression that we can match together, because of course if we have a lot of partial match, we have a lot of regular expression that are active in traversing the automaton. And this is a problem because we have to investigate and check whatever this regular expression can be keep active during the continuous of the traversal of the automaton.
Okay. Thank you, Filippo, for the talk. So I will stop sharing and I will pass the word for the next speaker,